Hello, my name is Ross Walker. I'm pleased to join you today to present our paper examining the future of automated plant in construction, a UK perspective. This paper is an example of industry and academia working closely together, and we draw on the experience of the client, National Highways, the contractor, Costain, research and development partners, Transport Research Laboratory, and academia through the University of Edinburgh. I'm Ross Walker and I'm representing the University of Edinburgh, and I will be presenting this paper today. The paper combines a literature review with direct industry data and presents a potential future for the deployment of plant on construction sites. It discusses how sites could evolve to accommodate the new role of CAP and how people and plant will need to work together to accommodate it. So, like many industries in the UK and across the globe, the UK construction industry faces a number of significant challenges, including the climate crisis, ageing workforce, and rising material costs. As ever, technology is presenting solutions in part to these problems, and as digital technology matures and machine learning and AI become more advanced, we see that automation of fleets of machines of construction sites are no longer some kind of sci-fi dream, but a possibility in the relatively near term. Plant typically refers to earth-moving machines, so excavators, dump trucks, etc., and these machines will continue to be a critical part of job sites. In reality, on today's connected site, as illustrated by this image, and future sites, plant really can refer to any apparatus or machine concerned with carrying out a construction activity, so we kind of need to extend the definition of plant to cover smaller, physically ancillary plants such as UAVs and other smaller robotics technologies that enable these larger machines to carry out their activities. So what are the benefits and what are the drivers? Why are we doing these things? And let's have a look at some of the bits and pieces in here. So there are a number of benefits. There's more than just listed here, but just to dive into a couple of them. Safety is almost always at the forefront of all construction activities within the UK. And so an example is 2018, 30 workers didn't go home as a result of a collision with a vehicle, piece of plant machinery, and thousands more suffered injuries which didn't result in deaths but can serious harm. Zero harm targets are something that most companies are kind of using to try and drive innovation towards a zero harm construction site where everyone goes home at the end of every day. So that's the first and primary one. So leading on from that is productivity, and other industries are ahead of the curve here. If you look at this chart, as we know, construction is hard to automate, which is the primary reason for the lag, and we'll discuss that a little bit later. But the interesting thing to note is where there's this kind of lag, there's this productivity opportunity, which is one of the other key drivers that we've got some way to go, but that some way to go should be seen as an opportunity. So there's two. So if we just, before we go into the future of plant, let's have a look at where we've kind of come from, and what we've seen is throughout history in terms of plant. It's a relatively new history in terms of the kind of plant that we think of today as being construction machines, but the type of machine that has been most prevalent has been basically dictated by the type of construction activity that's been undertaken. So a good example of this is the kind of boom of the motor scraper in the UK when the motorways were first being built. So in 1978 we had a peak of 48 million meters cubed of earth moved, and this dropped to 30 million meters cubed in 1984 as kind of we completed the main first rollout of major motorways in the UK. This idea has kind of led the way for the kind of advanced general purpose machine, or as we might commonly refer to it as the excavator. And obviously we see these as extremely popular machines due to their versatility in carrying out many tasks. And this is kind of further illustrated by CO2 figures and analysis. And there's some that was done by Danfoss in the UK here recently, which says that 92% of emissions are from machines over 10 tons, and of those machines, 50% of those are excavators. So, very popular type of machine. The versatility of these machines does mean that they are, by their nature, more difficult to fully automate. So that's one of the challenges that we've got to overcome. So let's deconstruct connected autonomous plant a bit. So the connected part refers to obviously the ability of a machine to kind of communicate with other plant and external networks and systems. So sharing information from onboard telematics supports, a wide range of uses. For example, reducing idling times, improving haul routes, etc. And it's very much a key enabler for automation. So you can't really have you can have connectivity without automation, but you can't have automation without connectivity. So, for example, technologies such as 5G networks in both a private ad hoc and permanent public form are now enabling automation and various other solutions. So if you look here, the first images of a site with Plinks 5G, first 5G site in the UK, and then secondly, and pretty excitingly, the CAP solution on the right there, where we essentially control the machine from 8,000 miles away from the UK in Arizona, and that's the kind of thing that the connectivity side of things is enabling. So the second part is obviously automation, the autonomy side. So it's important to distinguish the difference between automation and autonomy. Automation refers to the conversion of a task which is kind of typically carried out by a human to one which is carried out by a machine. And autonomy considers the capacity of a system to operate as an independent unit to complete a task without being controlled or manipulated by another system or human. So for many aspects of construction, the goal will be to establish an automated system to complete the task with no requirement that it operates independently. So that's just automated, or outside that defined and well understood operational constraints. So despite having made that distinction, the term autonomous is often used to cover both aspects when discussing both on-highway and off-highway vehicles. And I guess the autonomous part is intended to imply a direction of travel towards systems where we have a lack of any human role within in the operation of a machine. So now we know kind of what's meant by CAP. Let's have a look at why automating construction machines is hard. There's this idea called the operational design domain, which is essentially the environment and the conditions in which a piece of plant machinery can be expected to operate, or any vehicle or system for that matter. There's 4 reasons that are kind of identified in the literature that outline the challenges. So the first one is construction sites are kind of a variable size and form, and they're very much kind of project based. It's not like a factory where you've got a specific thing being made over and over again. Every project is in some way different. There are things that can be learned obviously from each, but they are inherently different in different locations geographically, etc. They're dynamic, always changing. So the operations are kind of concerned with altering the environment in some way, and they're also exposed to external factors. So weather, etc., that make them more difficult to kind of set those constraints through that operational design domain, unlike other kind of industries. So now we understand a bit about the challenges. We can look at the kind of broad approaches that we may see materialize in terms of automating plant. The first way is that the plant has relatively little perceptive and decision-making ability, but it's used in an environment with a kind of high-quality centralized control infrastructure. And this is a kind of real-time digital twin idea. And the second type is a kind of plant is equipped with a control system that's sufficiently perceptive enough and has kind of decision-making quality that can effectively mean it can be treated in the same way as a human-driven machine with minimal support from the infrastructure. So many existing off-highway automated systems centralize this control. So, for example, in mining, where you've got haul routes that don't really change very often, and where the projects span long durations. So there's an example there of mining in the bottom right. So linked to those two approaches then, we kind of hint in the paper that the approach that's more likely, due to the kind of more localized operations of off-highway driving, and a high level of accuracy, which we already map and kind of measure these environments. That the first, more centralized way is more likely. So on highway vehicles are designed to function on roads that have little or no dedicated infrastructure to automated driving. And this is because a significant challenge of providing the required infrastructure kind of would mean that these types of networks would be infeasible just because of the pure cost and challenge associated with that scale. Having said that, the kind of skill required by operators to conduct some of the more advanced tasks means that a lot of the kind of more general AI kind of research and learnings from that space will almost definitely be involved in creating a kind of fully automated general purpose construction machine. So yeah, here's the two examples of what these kind of infrastructure systems may look like. So as automation construction kind of continues to evolve, the human plant boundary and the interactions need to change to accommodate the new capabilities of the machines. So there are multiple aspects to this. Firstly, it's important to consider the safety elements of automated plant operating alongside humans. If one of the reasons for automating machines is to improve operator well-being and safety, clearly we need to ensure that that injury doesn't come from these machines as a result of kind of immature technology deployment or something like that. It's not to say that obviously CAP will be like a silver bullet that solves the zero harm problem. Rather, it needs to be kind of safer than the existing kind of standard. So again, kind of looking at this image of the connected site, we can see an example where there's an exclusion zone. An example would be, someone enters the exclusion zone, the machines stop. This is something that already exists. So the next bits of this project, we're presenting a taxonomy that classifies different autonomous machines and to what extent they're automated. We're presenting that at ITARC in July, and kind of later this year we'll bring in the third phase of the CAP project, where we'll look at design for machines and involving designers in the autonomy process, as well as legislation, which kind of is the most commonly cited barrier to adoption of this kind of technology, as well as also creating test beds for collaborative testing. So I've run over time a little bit, but please do email me with any questions, and thanks very much for listening.